Hi, welcome to this week 7 of lectures in this programming and data structures course. So this week we are going to explore the story of nonlinear data structures. Recall that over the last 6 weeks we started off with the role of programming, the role of recursion, writing recursive programs and understanding the role of recursion, and then we studied linear data structures. We have now written three programs. I mean, each of you have submitted three programming exercises on essentially using linear and almost linear looking data structures. And it's time to move on and look at nonlinear data structures, which are very powerful, which play a very central role in computer science. So, in these lectures this week, what we are going to do is we are going to look at the tree abstract data type. And once we look at the tree abstract data type, we will also look at what the primary usage of these data types are. And we will look at traversal algorithms. So if you want to access data in a tree, you have to traverse the tree, which means you have to go from one node to another node from a fixed starting point, which is called the root. And then we will look at special kinds of trees which are very important for designing other data structures that we will study during this course over the next couple of weeks. And we will also, as usual, look at some amount of code. And you would have already seen that over the last couple of weeks, the code is actually fairly simple. I hard code data inside the program just to give you a feeling of the compilation and the execution. And in any case, we look at the implementation of the different methods that we talk about associated with every data type. We'll do the same thing with the tree data type and the binary tree data type, and we will see what distinguishes the two of them and what are the different concepts that you need to keep in mind when you think of a binary tree and when you think of a tree. So what we do now in this first lecture this week is to look at the tree data type, and then we will look at the implementation of the methods associated with the tree data type and a simple programming exercise. The implementation of the programming exercise we will visit again about a couple of lectures from now. So let me now go to the presentation. All right, so we are going to talk about nonlinear data structures. We're going to start off with the simplest of these nonlinear data structures, that are trees. We are going to look at trees and binary trees. I won't define a binary tree or a tree now, but I will give you an example. The primary role of this data structure tree is to typically represent some form of grammatical information. So when I mean grammatical information, the structure of the tree says something about the values which are associated with the nodes of this tree. So as you can see, the tree has a structure, the tree has nodes, the nodes have values, and the structure, we will see what the structure of the tree is, tells us something about the relationship among the values which are in the nodes of the tree. The best way to do this is to start off with a simple example, and in almost all spoken languages, this grammatical structure, the grammatical structure of what constitutes a sentence is very important. For example, in the English grammar, a sentence is an object, and we know that every sentence has a subject, a predicate, and an object, and the predicate relates the subject and the object. For example, we can say Rama married Sita. Right? So clearly this is a sentence, right? And we saw that Rama is a subject and the predicate is married and the object is Sita. So this is a very simple example, and you can see that this pictorial representation that represents the rules associated with a sentence is intuitively appealing, right? So this picture in essence tells you that every sentence has a subject, a predicate, and an object. Right? So therefore one can imagine that this data structure stores the grammatical information associated with the concept called sentence, and the grammatical information regarding the concept sentence involves the subject concept, the predicate concept, and the object concept, right? And we refer to this pictorial object as a tree. Over the coming set of lectures, we will formalize the definition of a tree. We will also visualize the tree in a certain manner, and we will also see how to write programs which can create trees as in-memory data objects, that is, data objects which sit in the memory during execution, and how we will manipulate the trees, how we will actually visit different nodes of the trees, and so on and so forth. So that is the focus. So what are trees? Trees are abstract objects, right? They in some sense look like this. They have nodes. Each of these is called a node, right? And there is a value sitting inside a node, and there is a relationship between the nodes, and this relationship also encodes a relationship between the values which are sitting at the nodes, or values that have been placed at the nodes. We will get more precise as we go through, and we will also see how to define these trees in a programming language, and while execution, how to visualize the tree as a runtime object, right, manipulated by the program. These are the things that we are going to study when we talk about trees. All right. Of course, the word tree is not has not originated from computer science. Computer science is much younger than the concept of trees. And if you ask a non-computer scientist what a tree is, he or she will immediately agree that this is a tree. It has a single root, right? It has multiple branches, right? In this case, I have drawn like 2 arrows to indicate that more branches than the number of roots typically, and 3 arrows to indicate that there are many more leaves than the number of branches, and definitely more number of leaves than the total number of roots. So this is the nature's view of a tree, and this is a computer scientist's view of a tree, right? It's upside down. There is a single root, right? And there are multiple branches, but we also introduce this concept of nodes. Nodes are the places where the branches branch off, right? As you can see, these pink lines or violet lines actually go here, right? And this is a node, and to the left is a branch, to the right is a branch, and to the left is a branch. And the furthest entities from the root are really called leaves. That is, places from where there are no further branches, right, are special kinds of nodes, and they are called leaves. Now, what can you do with this computer scientist's view? One can actually keep track of the root and keep some values at the nodes, keep some values at every node, keep some values at the trees, keep some values at the leaves, and then manipulate this object. For example, we can eliminate some leaves, then we can add a few new nodes, we can add a few new leaves, and so on and so forth. This is a computer scientist's motivation for viewing this data object. Most importantly, the concept that you should keep in mind with respect to the computer scientist's view is that the tree seems to keep some hierarchical information. That is the most important thing. So what is a tree? As far as a computer scientist is concerned, it's a finite non-empty set of elements. Right? So first of all, it's finite. There are some number of elements, right? Definitely at least one element. It is a hierarchical object, right? So it's a model of a hierarchical object, and the elements are called nodes, right? That is the elements in a tree. If somebody asks you what are the elements in a tree, the answer is that these are nodes, right? The nodes have a position, right? And any pair of nodes have, so for every node there is a well-defined parent or a child relationship with another node. So what are the typical applications of trees? These are ways of representing organization charts, right, and some systemic information. The directory structure on your computer is also a classic example of a tree, and so on and so forth. So let's look at this picture. What does this picture say? This picture encodes some information about a concept called a university. Right? So university is a value which is sitting inside this node, and this node we are going to refer to as the root node. A university has students, a university has professors, a university has administrators. Students are of two kinds, undergraduate students and postgraduate students. And postgraduate students are of three kinds: students who are studying for a postgraduate diploma, students who are engaged in postgraduate research, and students who are obtaining a master's degree from a postgraduate study. Professors are also further classified into two kinds of people using the concepts of teaching professors and research professors. And these are the concepts that we have focused on, but observe that apart from the concept, there is the root node. There are three children of this root node, and this node has two children, and you can think of these two children as the grandchildren of the root node. And similarly, these two children as the grandchildren of the root node and children of this particular node. Observe, I am very carefully avoiding saying that UG is a descendant of university. That's a technically incorrect statement to make. The descendant and ancestor relationship that you might have studied, or the one that I'm going to tell you in the next couple of slides, is a relationship between the nodes and not the values. Of course, it is possible to visualize, and it is indeed correct to say that the value at a descendant is also a descendant of the value at the particular ancestral node. In other words, it is indeed not completely incorrect to say that UG is a descendant of university, but if you try to understand that sentence in English, it doesn't make sense. Right? So therefore, we will avoid coming up with ancestor-descendant relationship among the values, but we will always use ancestor-descendant relationships as structural relationships. So this is what a tree is. So let me summarize again. A tree has at least one element, and the elements are nodes. Right? The nodes contain values, the nodes contain data, and every node has a parent or a child relationship with some other node. Of course, some nodes have both parent and child relationships. For example, this node has a parent and this node even has a child. Of course, this node does not have children, but this node has a parent. The root node does not have a parent but has children. Now, observe that I have tried to communicate to you an abstraction of this object called a tree. How to use this is left to your imagination, and we will definitely look at a few examples, right? And we will use them in our programming exercises. As you can see, this is one example which uses the abstraction of a tree. All right, let's look at the terminology that I spoke about in the previous slide. Right? So a root node is one that doesn't have a parent. Sibling nodes are those that don't have. Sibling nodes are those nodes which share the same parent. An internal node is one that has at least a child. An external node, otherwise called a leaf node, is one that does not have children. The ancestors of a node, which are the parents, the grandparents, and the great-grandparents, and so on and so forth, are examples of ancestors of a node. The descendant, again, is a child. The grandchild, the great-grandchild are all examples of descendants of a node. The depth of a node, this is a numeric parameter associated with every node. It is a number of ancestors that the node has. The height of the whole tree is the maximum depth of any node. In this example, we will observe that, again, it's a numeric parameter. The height of the tree is 3. The root is at level 0. This node is at level 1. This node is at level 2. And this node is at level 3. Okay? And Therefore, the depth of a node is depth of this particular node, the node that contains the value k, is actually 3. The degree of a node is a number of its children in this case, and the degree of the tree is the maximum degree of its nodes. Right? So I've written something that's incorrect here. It's not the maximum number. The degree of a tree is the maximum degree of its nodes. That is a subtree of this tree. The region in violet is a subtree of this tree. It's a tree which consists of a node and its descendants. So let's do some small exercises here. You can see that E, I, J, K, G, H and D are all external nodes, otherwise called leaves, because they do not have any children. A, C, B and F are internal nodes. They all have children. A is a special node. It's a root. It does not have a parent. C and D are siblings. G and H are also siblings. Actually, B, C and D are siblings. K is a descendant of B. K is a descendant of F. K is also a descendant of A. K is not a descendant of C. And of course, one can say that K is a descendant of a sibling of C, which is correct. But K is not the descendant of every sibling of C. That is, K is not the descendant of D, but it's a descendant of B, and so on and so forth. So as you can see in this slide, the most important concept is not the values in the node. It is about the structural relationship that is among the elements of a tree. The elements of the tree are the nodes. Right? The nodes store values. Right? That we will come to shortly. So let us look at the short exercise about the tree properties. Right? Let us ask how many nodes are there in this tree. Right? As you can see, there are 6 plus 3, 9 nodes. What is the height of the tree? The height of the tree is that value which is the depth of the deepest node. Right? So let's look at the depth of the deepest node. A is at depth 0, B is at depth 1, this node is at depth 0, this node is at depth 1, 2, 3 and 4. Therefore the height of the tree is 4. The root node is this node, that is a node that contains the value A. Okay. The leaf nodes, as you can see, are the nodes that contain D, the nodes that contain H, the nodes that contain I, node that contains F and the node that contains C. The interior nodes, as you can see, are those which are not the leaves. Now similarly, you can write down the ancestor of the node that contains H. So the ancestor of the node that contains H are all these nodes, right from the nodes that contain A, the node that contains B, E and G, and so on and so forth. So it's a simple toy exercise, and since we have access to the slides, and we'll also put up a small exercise with this information. Now we are ready to talk about the specific data items that are associated with a tree and the methods associated with the tree. So let's look at the methods. Okay. The methods are the size of the tree, a Boolean query as to whether the tree is empty. We now make a very precise distinction between the elements and the positions. Okay. So when I say elements, the method returns the values which are at the nodes. And the method position returns a pointer to the list of all nodes. The accessor methods it returns a position. That is, when you ask for the root of a particular tree, you get a pointer to the root of the tree. The parent method takes as an argument a pointer and it returns a position which would be the parent of P. Of course, it should return an invalid query kind of a message if P is given to be the root, because the parent of P is undefined. We will come up with some conventions here. The children of P would return a pointer to the children of P. That is, this would be the return value of this method is a pointer to a list of nodes. That's what I've written as a position iterator. The query methods are queries like, is a node an internal node, or is it an external node, or is it a root? These are very easy to check. If the parent is not defined for a point for a node, then it is a root. If a node doesn't have a descendant, it is an external node or a leaf. Otherwise, it is an internal node. The root is also an internal node. Here are some update methods. We swap elements P and Q. Now remember that the elements are the values which are in the nodes. Therefore, when we swap elements P and Q, the values in the nodes P and Q are exchanged. The replace element at a particular node by an object O returns a value, whether depending on whether the object was successfully replaced or not. There are no limitations to the kind of methods that we include with any abstract data type, and this is more so this is very true with the tree abstract data type, because multiple users of the tree abstract data type come up with multiple methods. The delete method deletes a node from the tree, but it must also maintain a tree. Similarly, insert a node into the tree as the descendant, or insert it as a child of Q. That is, insert the node P as a child of Q and maintain the tree structure. These are all natural methods which update the structure of the tree. So as you can see, these are generic methods which ask for the values, ask for the positions, ask for data associated with the tree. These are accessor methods which tell you information about whether a node a node is a root of the tree, or whether and what its parent and children are. These are query methods which extract properties of different nodes in the tree, right? And here are the update methods which update the values which are stored in the tree. So therefore, over the last few slides, over the last 15 minutes, we have looked at pretty much everything that we need to know about the tree abstract data type to be able to use it. Let us look at an intuitive representation of a tree. So one of the most popular ways to visualize a tree is the list representation. So let us look at this particular list. Right? As you can see, the list contains further lists inside it. Right? So this whole list has multiple lists inside it. Right? So let us look at the multiple lists. For example, k comma l is a list. Just the element m is a list. Okay. Now you can see also this list whose elements are h, the list containing m, then the element I and the element j. That is, the elements in this particular list are the element h, the list containing the element m, the element I and the element j. So now I'm going to specify a tree using a recursive specification, right? And it is specified as follows. In a list, the root is the first element of the list. So every list now we are going to visualize. Now if a list is properly parenthesized, then the first element of the list is the root of the corresponding tree. The remaining elements of the list are the children and the subsequent descendants of the tree, of the root node. Sorry, let me say this again. Whenever you see a list which is properly parenthesized, the first element is the root of the tree that is represented by the list. The remaining elements in that list are the children of the root node, again specified recursively. So this rule is applied recursively. So let's look at this example. A is the root node of the tree, and now let us move towards the children, right? So this parenthesis starts here, and let us see where does it end. This is matched by this, and this matched by this. This is matched by this. This is matched by this. Then this is matched by this. Now you can see that this parenthesis matches this parenthesis. Therefore, A is the root with a single child, right? And that single child is a node B. And everything else is a descendant of B. It is either a child of B or a descendant of B. A is a ancestor of the node B or a parent of the node B, and A has exactly one child in this example, and it will always turn out that every node has a unique parent or zero parents. As you can see, every properly parenthesized list, right? I should not say properly parenthesized, but I'm saying this for redundancy. Every list is indeed representative of a tree. And how does one view a list as a tree? One views a list as a tree by thinking that the first element of the list is the root of the tree, and the descendants of the root are given by the remaining elements in the list. All right. So now we have looked at an intuitive way of thinking of a tree. Of course, this can immediately be converted also. Not just is this representation an intuitive representation, it is also a representation that can be converted into a implementation. So using the linked list concept, you can define a tree very precisely by recursively defining a list of lists. Now let us just look at what one can do with a tree in an abstract setting. So the tree consists of nodes, otherwise called positions. Right? Every node contains an object, which is the value or the useful information. That is a data item in this picture. And then it contains pointers to its children. So this is essentially the abstract view of a tree when you think of it as an in-memory object. Right? The earlier pictures of trees are pictures that are imagined by people across multiple domains. Right? So for example, a person who is maintaining information about a university structure may not be a computer programmer, but can still think about the information being organized in a tree. Similarly, a computational linguist, or not necessarily a computational linguist, a person studying any language, right, can think of a tree to be this particular object. A linked list is an in-memory representation, and this is a programmer's imagination of a tree. Right? So this is a node, this is a record, or this is a structure. There is one field to store a data, and in these examples there are 3 fields to store pointers. Okay? The pointers point to different children of this particular node. Here is a tree representation, which is just a slightly more elaborate way of representing the picture in this particular slide. So every node in the tree is represented by an object. The object stores an element. The element is a value. In this case, B is a value, A is a value, A is a value, D is a value, F is a value, E is a value, and so on. Okay. Then the node has a pointer to its unique parent. So in this case, this pointer goes to the parent. In other words, this node, which is violet in color containing the value A, has a unique parent, which is this node, which is completely colored blue and contains the value B. Observe that the parent field of this particular node has this empty set symbol. This basically says that this node is a root. Now this node, as you can see, has some information about the descendants of B. Right? In other words, the children of B are represented by this particular data object, which has pointers to this node, this has a pointer to this node, and this has a pointer to this node, and so on. So in particular, you can now see that the node that contains D has two children, and these two children are visualized here, right? And there are pointers to the corresponding nodes here. Therefore, these white boxes are pointers to nodes, and the colored boxes are nodes themselves. You can think of this as the in-memory data structure. You can visualize these pointers in this fashion. This arrow mark, like you imagine the value which is here, the other arrow marks kind of are pointers to other nodes. These are addresses, and so on and so forth. The abstract picture of this tree, which is the in-memory data structure, is this particular object. Right? So there are, as you can see, 6 nodes, and the values inside the nodes, the values stored by the nodes, are the values which are written inside the nodes in this abstract object. The previous slide actually was a realization of what is called the left child right sibling representation of a tree. So observe that A is the parent node. There is a pointer to the left child, which is another node which contains the value B, and B has a pointer to its child, but B itself has a pointer to its right sibling. Sibling is, remember, B and C are siblings if they share a common parent. So B keeps a pointer to its right sibling, C keeps a pointer to its right sibling. Therefore, it is unambiguous that A is the root node which has three children which are B, C and D. A remembers B and B remembers C, the right sibling, and C remembers D, its right sibling. Now D has a child which is called H. Right? H has a child which is called L. L does not have any right sibling, therefore H has only one child. D has H as a child and H has one right sibling which is called I, therefore D and I are the two children of H and I are the two children of D, and so on and so forth. So this is called the left child right sibling representation of a tree. Therefore, when we program this, we will definitely endeavor to program the left child right sibling representation, and when you write programs and if you're maintaining a tree, the left child right sibling representation is a good way to represent a tree. Actually, in our implementations, we'll also, though we have not mentioned this, there will be additional fields here for storing the parent pointer, which we have not listed here. But when you see the implementation, we have done that also. Actually, we here also maintain a doubly linked list. That is, not only does B know that C is its right sibling, C also knows that B is its left sibling. This is to ensure that we use all the power of the linear data structures that we have learned in the previous lectures. Alright, so what have we done so far? So we have really answered questions about what is a tree. Tree has structural relationships among nodes. What are the nodes there for? The nodes are there to store values. How does one actually visualize a tree? You can visualize a tree as an abstract object, or you can visualize a tree as an in-memory object. When you think of the tree as an in-memory object, you think of the values which are sitting at different fields in the structure associated with a node, and some of these values would be addresses, in other words pointers, and nodes are classified into different types. There is one unique node which is called the root node. There are multiple trees, there are multiple leaves and multiple internal nodes. Now one can naturally ask the question, what can one do with a tree? Of course, just in a jocular manner of speaking, what can you do with a biological tree? Well, you can climb it, right? You can extract fruits from it. Right? You can water the tree. You can populate the tree with more fruits by giving it more nutrients, right? Giving it a better environment to flower and fruit. What do you do with a tree as a computer scientist? You can store values in it, you can retrieve values from it, you can add nodes to the tree, you can delete nodes from the tree, you can answer questions about what values are there in the tree, you can answer questions about how many nodes are there in the tree, you can answer questions about who is a ancestor who is a descendant of a particular node in a tree, and so on and so forth. For all these operations on the tree, you should be able to climb the tree or climb down from the tree. If it was a biological tree, if you have to traverse the tree, if you want to be able to manipulate the tree data structure, we have to be able to traverse the tree. Now you can see that traversal is a common theme associated with data structures. Whenever you set up a data structure, you should be able to traverse the data structure. You should be able to move to a particular node and access the data item there. So you should be able to modify the data item. You should be able to check if a certain data item occurs at some node in the tree, therefore, or in the data structure. Therefore, central to data structures is the issue of traversing the data structure. Traversing meaning moving from one node to another node, or moving to a specified node, and so on and so forth. Therefore, for tree traversal, there are two main methods called the pre-order traversal and the post-order traversal. These are two methods which are different from the other methods that we have seen in the tree ADT. Of course, these are also part of the tree abstract data type. Right? These are called the pre-order traversal method and the post-order traversal method. These methods are defined recursively, and because these are traversal methods, the primary activity of a traversal method is to visit a node. The pre-order and the post-order traversal tell you in what order to visit different nodes in the tree, and these are specified recursively. So let us see what the pre-order traversal says. The pre-order traversal of a tree which is given access to the root pointer. So let me say this again. The pre-order traversal rule, right? The pre-order traversal rule takes as an argument a pointer to the root node in the tree. It visits the root node. Then it traverses in pre-order the children. That is, it does a pre-order traversal of the children subtrees of the root tree, the root pointer. And this recursion, as you can imagine, will go on till the traversal encounters a leaf. When it encounters a leaf, it returns from that recursive call and continues recursively traversing the tree in the pre-order fashion. Right? First root, then the children. The post-order traversal is interesting. You first traverse the children and then mark the root as visited. It's a standard confusion among many students. How can you, in the tree, visit the children without going through the root? Therefore, let me make the technically correct statement. A post-order traversal is at a particular node, which is the root, is recursively defined as follows. First, you traverse the children and then mark the root as visited. And then mark the root as visited. So I hope this is not confusing. Right? So on the other hand, in the pre-order traversal, when you visit the root node, you mark it as visited first. Then you go ahead and mark the children as visited in a pre-order fashion, or mark the descendants as visited in a pre-order fashion. Right? We will see the distinction when we run an example. So let us do this. Let us look at the pseudocode. Right? And we'll also see the order in which the nodes are marked as visited in the pre-order traversal. So the pre-order traversal V, right, is to visit V, and then for every child W of V, you do a pre-order traversal of W. Okay, so there is a small typographical error here. Yeah. There are multiple purposes of pre-order traversal. Right? So what you can do is to print the whole directory structure on your computer using a pre-order traversal of the whole directory structure. So let us look at this tree. Right? So this tree is probably interesting for any of you who aspires to be a top-class researcher. So if you want to become a top-class researcher, your motivation has to be to become famous, or to motivate Indian students, or maybe to motivate Indian students. You want to not only become famous, but you also want to motivate Indian students. To become a top-class researcher, what are the methods? You probably write GATE, and then you join a PhD at IIT Madras, and then you do a top research, and then you talk about your success story. So these are all what are done by a top class researcher. Right? So I hope you get the message that I hope some of you become top class researchers. Let us look at the order in which a pre-order traversal visits the nodes in the tree. It marks this node first as visited, then 2 as visited, then 3 as visited, then 4 as visited. Now it has finished visiting the whole subtree rooted at this particular node. Then it considers this subtree of the root, marks this as visited, then explores this subtree, then explores this subtree, then explores this subtree. Then this whole subtree is visited. Then it comes here, visits this subtree, the whole tree is visited, and the function exits. So the numbers associated with every node are the order in which they are marked as visited. Let us look at the post-order traversal. The numbering tells you the order in which the nodes are marked as visited. So this is the directory structure on my computer for this particular course. There is a directory of videos, there is a directory of code, there is a single file called lectures.txt which says what are the lectures that I want to give, and then this is the root directory which is the directory associated with the course. Here are the leaf nodes which are files, which are the videos. These are the different .h files, and this is the .c file which you have already seen. Let us look at the order in which a post-order traversal visits. Start at the root. You will mark this root as visited only when all the children are visited. Only after all the children are visited. Therefore, the first node that gets marked as visited is that node that is visited first and does not have any further children or descendants. That would be this file. It's marked as the first node as marked as visited. Then this is the second node that is marked as visited. After this whole subtree is now visited. So this is the third node that is visited. Now you observe that this is not still visited because these three children have not yet been visited. So these leaves get 4, 5, and 6. This gets 7. Then this gets visited as the 8th node in the tree. Then the root node gets visited. Right? So this is the post-order traversal, and really if you visualize this picture, it's very hard to forget it. Now, not only can you access the data items in this particular order, you will definitely have this question, why should I have these two ways to access the different data items in this node? Okay? These are very closely connected to maintaining arithmetic expressions in different formats, and you've already seen them in one particular presentation, and we will definitely explore them but not study them completely in detail. We'll do a couple of small exercises which point you to the application of these different traversal techniques. So that was really the whole presentation associated with the first week. Now let us go to the code. So these are the functions that I have with respect to the tree abstract data type. Let us look at the tree.h file, which is something that we religiously do. Okay. So we have defined a type which is called a node. Right? It has a single piece of data. In this case, we keep a character. Right? We keep a pointer to the parent. Remember that in the slides we said we won't keep a pointer to the parents, but now in the code I am keeping a pointer to the parent. Then the parent has, the node has a pointer to the parent. It also has a pointer to its leftmost child. And every node has a pointer to the right sibling and to the left sibling. So this is essentially, these two together essentially put node in a doubly linked list. Right? And the left child and the parent put it in a tree. Right? As you can see, by keeping track of 4 pointers, right, we really have this nonlinear data structure. Parent keeps a pointer to the parent, left child gives a pointer to the leftmost child, and every node keeps a pointer to its left sibling and a right sibling. Okay, so now what is a tree? The tree is known by its node, root, a pointer to its root, and the root is a pointer to an object of type node, and the size value is to keep track of how many nodes are there in the tree. So this is the tree.h. Let's look at the interface methods. All right. So the first method is to create a tree, which is what a programmer would want to do. Then you ask queries about the size of the tree. Then you check if the tree is empty. Then you check if given a tree T, you return a pointer to the root node, and given a pointer to a node, here we assume that it is inside a particular tree. We return a pointer to the parent node. Now these query methods tell you whether the node is an internal node or an external node, or is it a root node. The delete method, which we've really not implemented, but you will see the code for it, right, deletes a particular node from the tree. And the insert node takes a pointer to a tree, takes a pointer to a node that wants to be inserted, and a pointer to the parent. The end result of this is that the node n is inserted as a descendant, the first descendant of the parent, okay, in the tree T. Then we have traversal methods, which are pre-order and post-order, which starts at the root and traverses the tree in either the pre-order or the post-order function. These are the methods associated with the tree. Let's quickly go through the tree interface. Implementation of the tree interface methods. Okay. So let us just see what we do in the C programming language. We create a tree, it returns a pointer to tree. The way we do it is that we allocate a pointer to the size of the tree. Therefore, a node which is of type tree is created. The root node points to null. The size is kept as 0. That is, there are no data items there, and then you return a pointer to t. The query to size returns tPointer.size. Okay. This one tells you if the tree is empty or not by evaluating this comparison with the value 0. Then this one returns a pointer to the root node of the tree, which is always well defined. That is the way we have defined it. Then we return a node to the parent node, a pointer to the parent node, and we check if a node is a internal node. Remember that if a node is an internal node, then it has no children, in particular because the first of the children is always represented as a left child of node. You just have to check if left child is null. If left child is not null, then you can say that n is an internal node. If left child is null, then you can say that n is not an internal node. Similarly, external, a node which is not external is an internal node. Similarly, a root node is one whose parent is null. So here we have the implementation for the insert method. Since we are sharing the code with you, right, so you can take a look at the insert method. So I'm not really going to look at it, right? So basically the way to do it, let me tell you logically, is that you take the pointer tree, you take the value that you want to insert, you take a pointer to the node, right? Then you add the node as a parent, as a leftmost child of the parent node, and then you connect the right sibling to the left child of the parent. Right? So what do? You insert the node. How do you insert the node? You basically make it the left child of the parent node. Right? After making it the left child of the parent node, ensure that the original left child is now the right sibling of the new left child. So once you do this, you are done. So this is a delete implementation. You're welcome to take a look at it. We'll talk about it later. Okay. So pre-order, we really have implemented exactly the order in which we we just implemented almost exactly what we saw on the slides. It's just converted from pseudocode on the slide to C code in this file. Okay. So if it's at the root, you first print the data item there. Then what you do is you go to the descendant and do a pre-order traversal. And you do this pre-order traversal by visiting every right sibling starting from the leftmost node. Right? So therefore you look at the left child, that is temp, and while that is well defined, you do a pre-order traversal make a recursive call to pre-order traversal with temp. Once this pre-order traversal is completed, then you move to the right sibling of the node and start a pre-order traversal from there. Do this till it becomes none, and you recurse. This is the beauty of a recursive specification. Right? What looks like a complex task, right, is represented just in 7 to 8 lines of code. The post order does not require any major description, right? Even as much as we use to describe pre-order. Okay? So what you do is, so it's a recursive call. If you're at the root and the root does not have, if the root does not have any children, in this case, that is, it is a leaf, then you print the data item and return. Otherwise, you go to each of the children, right? You start off with the leftmost child, right? And you do a post-order traversal, okay, of all its children, right? And then move on to the right sibling and do a post-order traversal. So there is a small error here, though I've compiled it and everything. This is the right one. So that completes the implementation of all the tree methods, right? So let me just compile this. Right, the compilation has succeeded, and let us just look at the programming exercise. Okay. So essentially what we have written is, we have written an expression evaluator. Right? Of course, our usage of the expression evaluator is very simple. Right? So what we do is we first print the expression, right? And the way we print the expression is, it's a modification of the traversal techniques that we looked at. So all that we do is to just print a open parenthesis, okay, first before we go and visit the descendants of a particular node. So let's look at the main function. The expression that we have encoded is this expression. So let us just see this expression. The root node is plus. Okay. So now you can imagine that you can look at this expression, do a post-order traversal, and do a traversal and then evaluate the expression. Do a post-order traversal and then evaluate the whole expression. Okay. So we just populated the values here. So let us just look at the printed output. Okay, so the executable that we create is tree eval, right? And now I need to ensure that the tree methods .o file is included. The compilation is completed, and let us now. As you can see, the expression is really this. It is, the whole expression is parenthesized, right? It's 2 multiplied by 5 minus 1. Right? That is the 5 minus 1 is the innermost expression. The expression surrounding it is 2 multiplied by 5 minus 1, right? Plus the star 2, and the whole thing forms the expression. So this is obviously a slightly modified version of printing it out in a certain format, and then evaluating it using the post-order traversal technique. All right, so that brings to an end the first lecture on nonlinear data structures, and we've really looked at the whole story about the implementation of trees. We've looked at the motivation, we've looked at all the concepts associated with the tree, we've looked at the different methods, and we've seen an implementation of the methods. What I have done this time is that I've rushed through the C program just to show you that indeed the implementation is done and the executable works, and I show you a demo. This is to motivate you to go and try to do the implementation yourself by looking at just the video and the slides. Right? This is definitely not going to be a programming exercise. This must be a self-learning exercise that you must do. So when we meet next, we will look at binary trees, which are a special kind of trees, right? And we will look at the difference between binary trees and the trees that we have studied in this lecture. And in the subsequent lecture, we will look at some quick applications. That brings to an end this lecture. Thank you very much.